So now let me introduce you today's speaker. So Dr. Jeffrey Hyman is a staff scientist in the Earth and Environmental Science Division at Los Alamos National Laboratory. He got his PhD in applied mathematics from the University of Arizona in 2014 with a PhD minor in hydrology and water resources. And his research focuses on integrating applied mathematics with geoscience to advance our understanding of complex subsurface hydrological processes. And his research group seeks to uncover the connection between flow and transport properties and the underlying geological structure through detailed high-fidelity flow simulation, through large kilometer-scale fracture networks, and small explicit pore microstructure. He leads a team to develop novel tools and algorithms for computational geometry, stochastic processes, numerical analysis, high-performance computing, fluid dynamics, and structural geology. And he is the principal developer of EFN Works, a cutting-edge 3D discrete fracture network modeling suite. So today is going to talk about the interplay of multiple scales in fracture media on flow and transport properties. And of course, you can use the Q&A button to ask questions. Usually we ask questions at the end of the seminar unless it's something really quick. And you can use the chat to interact. And also this is the last seminar for this series. So Jeffrey, the virtual floor is yours. I'll stop sharing.
Let me get my slides up for everyone. Okay, can everyone see my slides? Can you hear me okay?
Yes.
All right, great. Yeah, so Anna, thank you so much for the introduction, and thank you all for the invitation to give this webinar series. It's quite an honor for me to do this. SIAM has been a home for me for a long time, and it's very grateful to have this opportunity. I want to talk to you today about some work that my group's been doing, trying to look at how the hierarchy of length scales in fractured media influences flow and transport properties. So what I mean by that is at the very macro scale, you can have like the network structure and density. You have a mesoscale where it's the fractures themselves, a micro scale where it's in fracture variability, and an even smaller like sub-fracture scale, which is going to be the matrix surrounding the rock. What we're going to do today is kind of start at a very high level, and we're going to work our way down to the micro scale, and we're going to see how each of these different length scales influences the flow dynamics and how they interplay with the length scales around them. So over here on the right side, we have an image of some azurite in a fractured system. So that's the blue, it's a chemical reaction passing through. This is an image that I got from Barb Dutrow, who's a professor at Louisiana State University, who's graciously allowed me to use it. What we see here is you have multiple scales in the fracture network. So you have these 3-4 major fractures that are cutting kind of vertically through the image. When you have some other fractures kind of coming across from the side. Within that, you also have variability in the kind of aperture of those fractures. So that's the width of the fracture, and as well as kind of the kind of intersections of how they connect with one another. So the scales, the actual like length scales we're going to be looking at today are much larger than this, but you can kind of see how those integrate within this one image. So we have the largest scale, which is what we're going to call the network scale, and that's roughly from kilometers down to about 100 meters. Then you have the fracture scale, which I'm going to say is about 100 meters down to the meter scale. My thresholds here are based on basically what we can image above 100 meters. You can actually like pick out individual fractures. Below that, 500 meters or below, it's much harder to pick out individual fractures, and we have to treat things somewhat stochastically. Below that, you have the in-fracture scale. So this would be aperture variability. There's a significant amount of work that's done on this. It's also known as fracture surface roughness, right? We're not going to be looking too much at like curvature of a fracture, but more just kind of the disparities caused along the surface due to the formation of the fractures. And below that, we have the sub-fracture scale, and that's going to be interaction with the surrounding matrix. So what we're looking at here are these 4 different tiers, and we're going to start looking at how they interplay with one another. So we're going to start off with the network scale. Then we're going to go to the fracture scale, the in-fracture scale, sub-fracture scale. We're going to look at the simulations being performed at each one of these different scales and how they can interact with one another and the feedback loops that start to form. To do this, we're going to be using a software package called DFNWorks, and I'm going to go through the kind of the nuts and bolts of the applied mathematics and the numerics behind this today. DFNWorks is broken up into three primary pieces. So there's DFNGen, which is what we use to generate the network and create a conforming Delaunay mesh. The reason why it's important that it's a conforming mesh is it makes the flow solving so much simpler. The reason that it's important that it's a Delaunay mesh is that the dual mesh of that is a Voronoi tessellation, which is in a certain sense optimal for two-point flux finite volume solvers, such as pFlowtran, which is what we're going to be using today to do our flow calculations. So why do we want a conforming isotropic Delaunay triangulation? Well, the conforming piece just makes solving the equation simpler. You don't have to have a conforming mesh when you're using a discrete fracture network. Discrete fracture networks are one modeling tool that we use for subsurface hydrology, where we represent the fractures as these two-dimensional planar objects that intersect with one another and form this complicated network. The reason why we treat them as two-dimensional or codimension one of a three-dimensional system is that they're so much longer than they are wide. And so we can essentially take that aperture field, the width of the fracture, and we're going to treat that as being essentially a planar structure. We make up for this in terms of the control volumes on the mesh by extruding them the size of the aperture. So the control volumes, where we're actually going to do our computation, are fully three-dimensional objects, but there's only lateral flow. So within a fracture plane, you have no flow going this way or this way, but you can have flow coming in and out of the control volumes. This is how we account for the actual volume that would be in the fracture, even though geometrically it's two-dimensional, okay? So being a conforming mesh means that the mesh on one fracture conforms to the mesh on another fracture. This is not strictly necessary. There's a lot of excellent work being done out there right now where people are using non-conforming mesh. You can use mortar methods or Lagrange multipliers, all sorts of different ways to essentially link the flow solvers or the flow solution on one fracture to another. The reason we're doing this is because we want to be using two-point flux finite volume solving codes, because those ones are locally volume and mass conservative. There's been a lot of work that's been done on them in the past 50 years. And so we can use these legacy codes to use all of the multi-physics that are there. We don't have to reconstruct the chemistry portions, the transport portions. Those are already built and we can just kind of use them out of the box. The isotropic is just to make things a little bit nicer of a mesh. If you have a nice isotropic Delaunay triangulation, your Voronoi cells are pretty plump, they're not very skewed, and it helps your solver in the end, right? One thing that we optionally do is we coarsen the mesh away from the fracture intersections. So near the intersections with other fractures, the mesh is very refined. This allows us to pick up high gradients in the flow, while away from it, the dynamics are, the physics and the kinematics that are occurring are a little bit less quick. The gradients are lower, so we can have a coarser mesh when we don't miss too much. One caveat with this that I want to point out is that's just for the flow solution. If you are doing Eulerian transport, or in particular reactive or geochemical transport, you would end up with variable numerical dispersion, and that would be very hard to get a handle on what is going to be physically real and what is a numerical kind of artifact imposed in the simulation. In that case, you'd probably want to end up using a uniform mesh, just so you know that your numerical dispersion is more or less the same everywhere. To do this conforming Delaunay triangulation, we use an algorithm that we developed called FRAM, which is the feature resampling algorithm for meshing, right? And that was put out in 2014, and it shows kind of how we do this conforming mesh generation. We extended this in 2022 with some summer student, where we ended up using a new Poisson disk sampling method for the mesh generation. This is much faster. Instead of kind of creeping up on getting this variable resolution, as we were doing before, you can do it directly. And there you can show some rigorous proofs of kind of how good of a covering, if you want to think about it that way, you can get with these different algorithms. The next piece of DFNWorks is DFNFlow. So this is how we're going to do our flow calculations, right? We're not going to use it for transport today. The way DFNWorks is built is you can swap out any given flow solver so long as certain constraints are made. So our three main ones are pFlowtran. This is a massively parallel multi-component reactive transport code. So this has been used on, tens, hundreds of thousands of processors. It's incredibly powerful, and we can basically link directly into that. A lot of energy has been put into P-Flowtran in terms of its reactive transport capabilities. And so that's something we really don't want to reinvent. We also can access the code called FEHM, or the Finite Element Heat and Mass Transfer Code, which was developed at Los Alamos. And a lot of the work that's put in here is on multi-phase and thermal flow. Both of these two codes are 2-point flux finite volume, right? But they have different physics that have been kind of verified within the pieces. FEHM is really good at phase changes and also thermodynamics. So the simulation here we have shown in the center is supercritical CO2 displacing water within a fracture network. The third flow solver that we integrate with is a code called a MONSI, which this is, we use this for multi-dimensional flow and transport. So what I mean by multi-dimensional is if you're doing a discrete fracture matrix simulation. This is different than a discrete fracture network, in that in the matrix simulation, you have a mesh of the matrix that surrounds the fractures. So the matrix mesh is 3-dimensional and the fractures are still 2-dimensional. So what you have here is this multi-dimensional hybrid system with 2 sets of governing equations that are essentially linked. So we do this with again, using a conforming meshing technique. This is not strictly necessary. People do this as well with a non-conforming mesh. We do it because, again, it simplifies the numeric, right? We take the energy and we put it into generating this nice mesh rather than on these other kind of like constraint parameters or like Lagrange multipliers, what have you. Okay. The third part, excuse me, the third part of DF and trans or DF and works that we're going to use today is something called DF and trans. So DF and trans is our Lagrangian particle tracking method. Essentially, we have passive tracer particles we can place into the system, and we see where they go as they vect through. They are non-reactive, they are passive, they do not interact with one another. Essentially, they just trace path lines through the system to give us a Lagrangian perspective on the domain. Okay. So we're going to start here at the network scale. So the question that we're going to look at first here is, how does the density of a fracture network influence flow channelization? And the key word I'm going to focus on here is density, because a lot of people talk about density of fracture networks, but they don't clearly define what they mean by that. I think heuristically or colloquially, we all kind of know if there's more fractures, it's denser, but how do we measure that? To do that, we use a percolation theory. So we're going to have a critical percolation parameter. This is going to be P, which is our number of fractures over the length of the domain squared, integrated against our PDF of fractures times the minimum between our exponent alpha and our radius, right? For our distribution, we're going to be taking a truncated power law, right? Distribution here with a minimum cutoff of R naught and an upper cutoff of RU. Now, P critical is this percolation parameter where you can put in for any set of parameters, right? We get a P back out. And P critical is the value where this equals 1, which means that there is almost surely a connected cluster of fractures that spans your domain. This critical percolation then allows us to put other densities or numbers of fractures we put into the domain, controlled by this value n, into a relative sense relative to that critical percolation. So what we're going to look at today is P prime, which is the number integrated out of here of PC, right, of 2, 3, 5, and 10. So essentially we're looking at twice the critical percolation, 3 times, 5 times, and 10 times in terms of the number of fractures. What does this look like, just for some intuition? So for P prime equals 2, we have this network in the top left corner. What you see here is we have one kind of primary channel of fractures coming through. P3, we have a slightly larger cluster. P5, we're filling up the domain. And P10, this is a fairly dense network. So the key here is that we have this kind of relative metric that then we can compare between different systems. Okay. Now, the other part of our main question here is, how does the density of the fracture network influence flow channeling? So flow channeling is something that I think we all know when we see it, but it's somewhat difficult for us to measure. So we're going to start looking at the flow equations that we're going to be using now. The first one is the Reynolds equation. Essentially, we're just saying that the flow through the network is going to be is governed by this equation, which is the aperture of each fracture cubed times the gradient, right? And we take the divergence. That's essentially just a Laplace equation, but our coefficient is the local aperture. In our network, we're going to have the apertures be perfectly correlated with the fracture size using this relationship. What this means is that R here is our fracture radius, and essentially the aperture increases as the square of the fracture radius with a coefficient. Okay. Now, physically, what this means is bigger fractures get larger apertures, but they don't, rise linearly. It's kind of sublinearly with the square root. Okay. Now, to measure flow channelization, what we're going to do is we're going to introduce two different terms. The first one here is something called P32. P32 is also known as the fracture intensity, and it's the total surface area of the fractures over the volume. So this has dimensions of 1 over length. Okay. From the other piece we're going to look at is something called a flow channeling density indicator, where we have this additional term, QF, which is the volumetric exchange of one fracture with its neighbors. But it's not quite that because of mass balance, that has to equal 0. So it's 1/2 times the absolute value of that. It's essentially a measure of how much flow is being passed through that fracture with its neighbors. We scale that with the surface area of the fracture, right? And then when you put it into this ratio, it's something called a participation ratio. Now, a key thing to notice here is that if QF equals 1, DQ equals P32. What that means is that if all of my flow is uniform between all my fractures, I essentially have flow uniform through the domain, right? And my ratio of DQ over P32 will be 1, okay? That would indicate essentially an active surface area of 1 or a ratio. Now, if my flow is very channelized, right? So only a few fractures have QF values that are significant, my DQ value will be lower and I will have a lower participation ratio. Okay, so we're gonna be looking at DQ over P32. In addition to the Eulerian points of view, we're also gonna be looking at a Lagrangian point of view. So here we're gonna follow our path lines through the system. This is what I was talking about with diff and trans, right? So our particles simply follow this advection equation. So they have an initial position of A in the domain at a time 0. And then they just follow path lines through the system according to the internal velocity field. Okay. Now, there's a problem here because I told you that we're using 2-point flux approximations for the flow, right? And what that gives us is our volumetric flow components in and out of the control volumes. It does not give us a velocity. So if our governing equations, right, are Q, right, is equal to B cubed or times the gradient of hydraulic head. So this is our kind of Reynolds equation when we take this to be divergence free. We have a trajectory equation, right? We need a velocity, but the problem is that we're only giving these normal components of the flux at each face. So the first thing we need to do is actually reconstruct the velocity. So given that we have this equation satisfied up here, this is essentially our Darcy flow equation, right? And our ins and outs equal 0. We have to then take the volumetric flow rates and essentially project them onto what is going to be our normal velocity. So again, the fractures are 2-dimensional planar structures, okay? So we need to build up this overdetermined linear system where essentially we're dotting the normal of the volumetric flow rate vector across a face with the direction coming out from the centroid. This gives us essentially an overdetermined system that we have to solve. And then we do a least squares or a pseudo inverse of it. And that actually can back out Q of F with just the two normal X and Y components. Okay, so that's how we go from this unstructured mesh with volumetric flow rates coming in and out of each control volume to a velocity that our particles can then advect through. Okay, so that's what this looks like. So here's a single fracture. Here's our velocity vector field. Okay, intersection. The black lines here are pressure contours. Okay, and what you have here is this kind of nice circular structure. What I want to point out here, because I think this is a very interesting point, is that this is a dead end fracture, right? So essentially, in conventional wisdom, there should be no flow here, but clearly there's flow and there's actually recirculation flow. There's a separatrix in the flow right here. It's incredibly complicated, which I think is just brilliant. So we get to see a lot more interesting dynamics that are occurring just from the kind of a velocity reconstruction piece. Okay. So now if we have that velocity field, simply solving that ODE gives us that our current position is equal to our initial position and the integration across the velocity field along our path line. Okay. Now, I really like this quote from Stephen Wiggins, who's if you know dynamical systems, he's fantastic books in Springer all about this. And it's let us note that in the study of ordinary differential equations, one might believe the problem to be finished when the solution, x, is found. On the contrary, that's when the story begins to get really interesting. What's wonderful about where we're at right now within our modeling capabilities is we can start to look at this very detailed Lagrangian point of view and particle point of view of what's happening in fractured systems, okay? So even though we have, the solution, quote unquote, of these ODEs, we can now really dig into that and understand more and more about the system. And that's the tool we're going to use to understand this kind of density relationship to flow channeling at the network scale. Okay. These are what the path lines look like within the fractured network. So each one of these lines is an individual particle trajectory. They're colored according to the velocity. And you can see here you have kind of a divergence in the flow, and then it converges at this intersection. As the flow converges, mass conservation and volume conservation forces them to speed up. And you have more flow going into a restricted region, so it has to go faster. And we can go and query these things throughout the entire network and begin to understand how the structure of the network is influencing these flow dynamics. Yeah. So the next piece we have here is we're going to construct something called a flow topology graph. Now, flow topology graphs are this really neat construction where we can take information from the particle trajectories, we can integrate it with the structure of the network, and then we can embed that all in a graph. Now, what I mean by a graph here is essentially something from network science, right? I think we all interact with these every day. So let's say we're on Instagram, I'm there, right? I have my account, let's say I have my friends, each one of them has an account, and if we follow each other, that would be kind of how the network is set up. So there, each one of us would be a node in the graph, and there's an edge if we follow one another, okay? We can do the same thing with particle trajectories and these fractures, right? So what we have here is our network over here to the left, and the fractures are colored from 1 to 10, and then over here on the right, we have our induced graph. We have our source node, which is where we inject particles. And what it says is that particles are going into fractures 5, 8, 9, and 10, okay? So we have a directed graph. Now we can see here from fracture 8, particles go into 6 and some come back to 8. So it's not acyclical. Particles can leave into a fracture and come back from it. So that was that recirculation that we saw a few slides ago, right? Now we build out and we can see the propagation of flow through the whole system. What it does, what the flow topology graph offers us, is the ability to look at a very complicated simulation, trajectories going every which way, and we have this nice mathematical construct that we can now query and begin to understand our system a little better. Now, explicitly, how we're going to make this graph, right, is the following way. So we're going to have one set F, and this is the set of fractures, right? And we're going to have a graph G, right? We're going to define a mapping phi, which maps F into the vertices of the graph. These are in the set V. Okay, sorry. The graph is called G, not V, right? So that's our first equation here, which is phi, which maps individual fractures to individual nodes. And then we say if two fractures intersect with one another, then there's an edge in our edge set that indicates that those two nodes intersect in the graph. Think about this way is that if two fractures intersect, each one's a node. If they intersect, there's an edge, okay? Now, what we also want to do is we also want to include source and target vertices into G. So we have an orientation of flow direction, right? So what we say is that every fracture that intersects our inflow node is going to get attached to an additional node. And we're going to call this S for source. Every fracture that intersects our outflow plane is going to get attached to another node, which is called T for target. Now, just kind of a fun thing here, you can show that this mapping is 1-to-1 and onto. For every fracture you have, there's a single, for every node in the graph, there's a single fracture that goes to it, and vice versa coming back. So it's bijective, right? It's 1-to-1 and onto. It's nice when you actually get to show these things a little bit more rigorously. Okay. So now, what does that look like in terms of our larger networks? Okay, so we've built a lot of machinery here. Now let's take it back to the more complicated physical problem. So for our very low density network, this is P prime equals 2, right? What we have here is our flow topology graph that looks like the following. Here, I've indicated the inflow by a green triangle and the outflow by a red square, or a red, red circle, sorry. Here, I've made the edges, the width of the edges in the graph proportional to the amount of particles that go through. And I've also made the size of the node proportional to the number of particles that go through. So what you can see here is that there's a major channel that passes through from the source to the target. And then off of that, there's not a whole lot of flow. Then you also have, for p equals 3, you have one primary channel, but then a lot of particles break off in the secondary channel. For p equals 5, the domain becomes much more dispersed. We see a lot of particles going every which way. And for p equals 10, it looks much more homogeneous, right? So this is a way that we can now take these particle trajectories, we can embed them into a graph, and we can start to understand what's happening within the system. Now, in terms of how we would measure channelization from this, we introduced this new metric, which what it does is it finds the shortest path in your system, right? And doing that with a weight where it's 1 over the number of particles that pass through, okay? Using the reciprocal allows us to find the edges that would have the most particles passing through have the lowest weight. And so the shortest path algorithm like Dijkstra's picks those up. We can then rank the shortest paths. We're going to do that by the superscript K. So we have the shortest, the second, the blah, 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 blah. And so then we can start to look at how the mass transported along each of those paths decays with increasing K value. So our quantitative metrics that we have here are the Eulerian flow channeling metric. So this was the one that was the active surface area ratio, that's dq over p32, right? And we also have our Lagrangian metrics, okay? So for p prime, for p equals 2, we have very, very low flow channeling or active surface area, indicating that the flow is highly channelized. As you increase the density of the network, right, you see that active surface area increases to almost 60%. The error bars here, or the variance bars, these are for an ensemble of, I think, 10 or 30 networks apiece for each of the densities, okay? In terms of the Lagrangian metric, so this is that flow path channeling indicator, right? What we see is a very rapid decrease for p equals 2, right? Indicating that the majority of the flow happens in 1 or 2 paths, and then these secondary paths, there's not a whole lot of flow in there. For p equals 3, we see kind of a slower decay, indicating the flow is somewhat channelized. And for p equals 5 and 10, essentially we see that the flow in the primaries and the secondaries is more or less the same. So we would say the flow there is not highly channelized. So what does this mean about how density of a fraction network influences flow channeling? So in general, network scale flow channeling decreases as the network density increases. This is what we saw from the flow topology graphs, and our metrics that we introduced also indicated this. Why does this happen? Is that as the density increases, there's more paths between the inflow and the outflow boundary, and so the flow field becomes less physically constrained. If you have a very sparse network, the flow has to occur in a few certain places. If you have a very dense network, there's a lot of connectivity and it can disperse, okay? Now, what we see also is that at low densities, there's more uniform flow within the entire connected network than in high density networks. So even though the flow is more uniform, it's still channelized. So heterogeneous flow does not actually indicate that you have highly channelized flow, right? It can just be more variation, okay? The next scale that we're gonna look at here is the individual fracture scale. All right, and so what we wanna look at here is how do changes in the local hydraulic aperture influence flow channelization. Okay, so what we're going to do here is we're going to apply a background stress field to our domain, and we're going to see how that changes the local aperture and then how that changes our flow. Okay, what we're going to, so as many of you are aware, actually solving fully coupled hydromechanical system in these fraction networks is incredibly challenging. That's not what we're doing. We're going to do something of a projection method, where we're going to have a background stress tensor, and then on each individual fracture, we're going to essentially project that stress tensor onto the fracture based on its normal vectors. That's going to be this part here, right? And then we're going to see essentially how much stress is placed on that fracture, right? The normal component is given by this classical term here, where B naught is our initial aperture. In the shear direction, we're going to assume a perfectly elastic model with more Coulomb failure, right? Where essentially what happens is if you stress a fracture enough, it can fail, and then it will slip and will dilate. Just to kind of give an idea of what this looks like, right? So we have compression and dilation, an initial fracture. So we have a fracture network with 3 Cartesian axes, right? As far as the principal directions of those 3 families. Here we're going to compress from the vertical, and we see that fractures whose normal vector is projected on this sphere compress. That's what the red indicates. While those that are off diagonal end up being dilated just a little bit, okay? Now, what we want to look at here is as we stress the fracture network from different directions, right? How do the fractures compress and how do they dilate? So in A and B, what we have here is isotropic stress. So you can see the stress in this little kind of axes here, right? The size or thickness of each of these bars indicates the magnitude of the stress from the tensor, okay? So this is 1 megapascal along the diagonal. This is 5. And what we see there is compression. And then if we go to 5 megapascal, we see more compression of all fractures. And this makes sense. Everyone's being squeezed uniformly. They should all compress, okay? Now we have 3 different directions where we have 1 principal stress and 2 not unstressed. As we compress from the top, we see that fractures that are aligned or whose normal is oriented with the primary direction of stress close. Same for the other 2 directions. But those that are tangential or parallel, not tangential, sorry, those that are parallel to that stress will actually open. So you see some fractures close, right? Some fractures open, depending on their orientation relative to the stress field. So what happens to the distribution of apertures in the system? So the teal line here is our reference case. This is unstressed. The blue is if we stress with 1 megapascal uniformly, isotropically, we see a decrease in the peak and a slight widening or narrowing of the distribution. If we go by 5, we see an extreme decrease in the peak and narrowing. Okay, so the fractures are actually getting slightly more uniform in their apertures. When we stress from different directions, they all look about the same. And when we stress in 2 directions, so we have like X and Y being 5 megapascals and Z being 1 megapascal, again, they all look about the same. Now, what's curious here is they don't affect the flow properties the same. To identify how they're doing that, we're going to go back to our graph representation, and we're going to start to query something called a backbone. Now, the backbone you can think about as being the first and second shortest paths using the flow topology graph. So back to our flow topology graph, we'd say our backbone here is from the source to the 5th fracture to 2 to 1 to 7 and out of the domain. What's really fascinating here is there's a lot of different ways you can pull out this backbone. We're going to be using kind of the simplest way, which is just finding a few of the shortest paths using these weighted edges that are the edges being weighted by the proportion of particles passing through each edge. And then we can go back and we can look at the fracture network that is the backbone. You can do this in large networks, right? And you can see kind of the flow channelization. So instead of looking at this and where particles go and they don't go, it's much easier to see the path lines that are passing through each of these individual ones. Okay. So now for our network, this is the one that we're starting to stress. This is what our initial backbone looks like. So what does it look like under different stress regimes? A, this is our reference case. This is our initial backbone for the system, okay? B, this is if we're stressing in Z as the largest magnitude. Here, our inflow is the triangle, outflow square. And we see that we have our primary channel that still has to pass through a few fractures that compress, as indicated by being red. Here, I've only scaled the fracture size by number of particles that go through instead of the edges. It's just a little bit too difficult to see. Here in C, right? So this is if you're stressing in the Y direction, right? We still have a lot of compression on some fractures, right? What's really curious is that in this one, in D, right, when we stress from in the X direction and don't stress as much in Y and Z, we have a path that goes from the inflow to the outflow that never touches a compressed fracture. So what that means is that we've actually formed, due to this kind of mesoscale piece, a fast path through the network. So how this influences our breakthrough curve, so these are travel time distributions of particles passing through the system, is very curious. So the first one is at the teal, right? This is our reference case. If we compress isotropically, we see a decrease in time. And again, as we compress more. So think back to those aperture distributions, right? Where you had, the mean aperture was just decreasing with compression. So this makes sense, right? As you decrease the aperture uniformly across the network, you should see a delay in travel times. Okay. Now we have these ones where we're compressing in different directions. So the teal is the unstressed. And we had the two where we didn't see much of a change in the backbone. We still had to go through some compressive fractures, those delay. But what's really fascinating is that you have this one case where now, because you stress in a particular orientation, you have anomalously early breakthrough. Essentially, the stress effects have caused this thing to open, and they've caused a fast path to form through the network. When you stress from all different directions, everyone basically gets compressed again, and you just see a large delay. So what this means is that the isotropic stress regimes don't alter the structure of the flow field very much, but we do see a monotonic decrease in high velocity zones within the network. When we stress it anisotropically, the flow can be completely restructured within the system. And this is really fascinating because what it means is that you can have this scale bridging effect where changes at the mesoscale influence the macro scale flow structure. We see a broadening of aperture distributions and big changes in the early arrival times, right? But mostly we see a delayed arrival time and long tailing, okay? So what we're seeing here is the network scale influences the fracture scale, and now the fracture scale is influencing the network scale in terms of the flow structure. Our next one we're going to look at is the in-fracture variability scale. So fractures are not parallel planes, right? We know this. There's a lot of wonderful work that's being done out there, both in the laboratory setting, the single fracture scale, and direct numerical simulations of flow through like profilometry images of these fractures, okay? We want to understand how that variability at the single fracture scale influences things at the network scale. To do this, we're going to integrate in with laboratory experiments. So this is a core of Marcellus shale. It's about 5 centimeter diameter that my colleagues in our rock mechanics laboratory broke, right? So they've formed a fracture in the middle of it. In situ, still under pressure, we were able to get X-ray tomography of the fracture, and that's the surface that you see here. We integrated that field down into a 2-dimensional aperture field. That's what you see here. We took one slice out of the middle of it, and that's what the distribution looks like. So you have quite a few very, very small apertures. These can be considered like close-off, pinch-off points. And then you have what you could convince yourself is an almost normal distribution of apertures. What we do is we take that aperture field, that 2D field, and we project it directly onto the fractures in the system, right? So numerically, what we're doing is essentially a random sampling of that field, and then we're projecting it so we can have variable apertures within the system. Now, before we were talking about those Voronoi control volumes, they were uniform in a fracture. We just gave them a different scaled volume based on that. Now we have cell-based different variations. So if you've ever seen, the columnar basalt, how it kind of rises and falls, you can think of essentially we have different variable heights that are passing through this system, different volumes of which flow can come in and out of, okay? Now what that does to the particle trajectories is fascinating. So here we have a control case of uniform aperture, and you see nice smooth trajectories, right? They come in, they pass through, right? It looks fairly straightforward. When you start including highly variable apertures, you get very tortuous and a lot of variability along the a lot of variability in the normalized velocity along each of the path lines. Okay, so the question then becomes, how does this influence, say, like our flow topology graph? So for the constant aperture, this is what our backbone of our system looks like, right? This is our flow topology graph. And you see major differences that start occurring due to the internal aperture variability. So like I said, we sample the field stochastically. So we do this in ensemble. So each one of these is just a different realization where we're sampling different parts of the aperture field and putting it on different parts of the network. In some cases, we don't see a major change in the flow structure. In other cases, we see massive restructuring of the flow field. So this is really curious, right? It's showing us that these in-fracture variability rescalings can actually, or in-fracture variability features can actually influence macro scale behavior within the network. It's not saying they always do that, but it's saying that they can. Now, what does this do to our kind of more common physical metrics? So if we look at our breakthrough curves, right? So the blue here is constant, all right? Over 30 different network structures, right? We have a tailing behavior of 10, or we have a tailing behavior that scales as minus 2.6. When we include variability, we end up with minus 2.3. So it's decaying slightly slower, okay? So we have more variability in the velocity field. Particles are moving a little slower through the system. We also see a widening of the peak, and we also see early arrival. So in all senses, this has become slightly more anomalous, more un-Gaussian. It's very curious how this is affecting it. In terms of the tortuosity, I'm measuring the tortuosity here as the path line distance over the linear distance between the endpoints, okay? And in almost all of the cases, the average tortuosity is larger when you increase variability, and the variance of the distribution is also wider. The active surface area, right? So this is that DQ over P32 decreases, right? With the variable relative to the active surface area. And then if you look at the flow channeling metrics, this is just DQ, you see a significant increase up to 300% larger flow channelization in the network due to aperture variability. So these are pretty substantial changes in macro scale flow properties due to micro scale changes in the fracture network structure. So that means that these aperture variability can be a major influence on the flow field structure, right? Does it mean that it will always be? No, that's not what we're getting at here. We need to do a lot more kind of experimentation and simulations where we'll be doing synthetic surfaces, and we'll be looking at different roughness coefficients, different variances, different fields to understand what are the critical values. So you can say it does not affect or it does affect these macro scale properties. All right, so what we're seeing now is that the network scale imposes the structure on the fracture and the infracture, but now the infracture scale can change the fracture network scale, like the fracture flow properties and the network flow properties. So we're seeing this feedback loops that are starting to form within our system. The last one we're going to talk about today is the sub-fracture scale. So for that, I want to talk about essentially how do we include matrix diffusion. By that, I mean particles are going through the domain and they can at some point diffuse into the matrix where they'll be retained for a given amount of time, and then they come back out. So if you consider just a pulse injection into a single fracture with an aperture B, the PDF of travel times is this essentially a Levy distribution, right? Now, what this is saying is, what I want you to focus on here is this kind of classic piece here, which is that it should scale as something of 3 halves, okay? We have a parameter A, which integrates the matrix porosity, diffusion coefficient, and the aperture B. And essentially, this is what our PDF of travel time should look like. This was done in the 1970s by Malowski and Zuber. And we're going to start with that to try to, how do we include this delay time of a particle advecting into the diffusing into the matrix and then coming back out. So if you take that PDF and you integrate it, you can get this CDF, and then you can use an inverse CDF sampling method, where essentially we can say our advective time, right? We can use that along with the inverse CDF sampling to then get back a total time. So this term here represents the matrix diffusion time. So we just do kind of a linear superposition. We advect a particle, we sample this time from this inverse complementary error function, right? We have the scaling parameter A, right, which includes the matrix porosity, matrix diffusivity, and the aperture. And then that gives us essentially a time domain random walk for the particles to include matrix diffusion. So what happens when we do that? So on the left side here, I have what is a advective curve in blue, right? And we're scaling at minus 2.85. And then when we include matrix diffusion, what we see is we recover that 3 halves. Remember that 3 halves that I talked to you about a second ago? In all cases, depending on if we change these values, we end up, the diffusivity values, we end up with that 3 halves. Now, what's curious is that if we have a slower scaling advective, so minus 1.67, we don't see the 3 halves, we see minus 1.35. And so we want to understand physically what's happening here that we're not recovering classic matrix diffusion. Okay, so the total travel time of particles undergoing advection and matrix diffusion through the network can be formulated in the following way, where we have that conditional probability. This is our Levy distribution from a few slides back, and then our advective travel time. So what we've seen in a few other of the breakthrough curves is that the travel time looks somewhat power law or is a Pareto distribution. So that's this term back out here. We combine this all and it gives us what is roughly going to be the breakthrough curve under these conditions, okay? Now, this, the two terms is essentially another Levy distribution, okay? And Levy distributions are stable distributions. And so essentially as our scale parameter goes to 0, we're going to recover a direct delta function. And then P of t is basically proportional to our initial advective term. What that means, right, is we can do some sort of asymptotic expansion and a Maclaurin series, right? That then allows us to expand this out, okay? So when we do that, right, we end up with this incomplete gamma function. And now as we expand the incomplete gamma function, we see 2 alternative decay rates. The first one is that if we're in very small diffusion lengths, we should recover advective travel times, okay? That means essentially the particles haven't gone far enough that they've been exposed to enough matrix diffusion. We should just see advective behavior. Now, what's curious is as the particles go far enough down, we actually see 2 limiting behaviors. The first one is that if we're decaying sufficiently fast in terms of our Pareto distribution, that's based on this term alpha here, we should recover the 3 halves. And if we're decaying relatively slowly in terms of our advective, we recover a different exponent, which is -1 plus alpha over 2. So what we did is we ran a whole big ensemble of a lot of different networks with different matrix diffusivities, matrix porosities, and we computed the slopes of those empirical breakthrough curves, and we compared them to the theoretical decay curves. And that's on this 1-to-1 plot here. So log alpha, right? So remember the critical point for alpha was alpha equals 1. So that's 0 here. If it's greater than log alpha equals 0, it should be 3 halves. And we see an excellent match, right? The larger the circle is here, the larger the A value, essentially the stronger the matrix diffusion. Now, if we have a whole bunch of other empirical decay rates, they match our theory pretty dang well, right? So what's that showing us is you have this relative battle between the advection that's happening, which is the result of all of these different length scales interacting together, and the matrix diffusion, which is causing this delay term, okay? So even at the subgrid scale process, things that are in the matrix, you can end up kind of washing out and influencing all of this other behavior that's occurring at the different length scales. So what I wanted to kind of highlight today is that with how good our numerical models are becoming for fraction networks, we can do so much. We can integrate in with laboratory experiments like I showed. We can create incredibly complicated networks. We can start to include stress, matrix diffusion, chemical reactions, which I didn't talk about today. But it's a question of what are the most important physical processes, right? It almost feels like within the applied math community, we're really far ahead in terms of like order of accuracy in our numerics, but we're missing who needs what, right? So what are the physical processes that we really need? How do we deal with coupled processes? The only coupled process I really talked about was mechanical. And the issue there is that wasn't even fully coupled, right? That was a quasi-steady state. And that's kind of what we can do in these complicated networks. So how do we actually bring in the coupled processes and build our numerical models to address those, okay? How important is the numerical fidelity and order of accuracy of our models when the uncertainty in these systems is so incredibly high? Everything I showed you today had to be done in a statistical ensemble framework because there's so much variability and uncertainty in how we generate the networks. So that part needs to be addressed too. And then also, once we have all these simulations, how do we analyze the results? I mean, it's great to make pretty pictures, right? But we need to be quantitative about that. And I hope I convinced you of that with like using the Eulerian or Lagrangian flow channeling metric, that we can use these tools in different ways to probe different pieces of the simulations to understand these pieces. On top of that, uncertainty quantification, rigorous UQ has to be a part of what we do in these systems. It needs to go beyond just simple error bars and confidence intervals that I've shown today. Okay, and so then how do we kind of integrate all these different pieces to do multi-model and multi-fidelity approaches? So for example, you can have a really high fidelity model, but could you do a low fidelity, like a pipe network model of these fraction networks? And could you use those two together to kind of flush out your ensemble in your space? So I want to thank all of my collaborators. I don't do this stuff alone, right? I have a wonderful team at Los Alamos, composed with Hari Viswanathan, Carl Gable, just retired, Satish Kara, he went to PNNL, so but he's still working with us, Natalia Makdonska, Eric Hagberg, and Matthew Sweeney. These are wonderful collaborators I've been working with for years, and so much of the work here today that I presented was theirs, and I'm really grateful to have the opportunity to share that with you today. On top of that, of course, there are those who supported all of the projects. Los Alamos National Laboratory, working with colleagues at UTEP, Colorado School of Mines, the Department of Energy helps fund us, and the Department of Energy, the Nuclear Energy, the Department of Nuclear Energy for like spent waste fuel disposal. If you're interested in our software, DFNWorks, please check us out. If you're interested in just questions and such, email us at dfnworks@nile.gov. And thank you everyone for visiting. And those of you in the future who are seeing this later on, I hope things are well. Yeah, and thank you all so much for your attention. I appreciate it.
Well, thank you very much for your talk. It's really interesting and the results are definitely impressive. So let's see if we have questions from the audience. Richard, would you like to ask your question live, or should I read it? So it says, given the results from the tests with flow through fracture over rough surfaces, can you comment on the feasibility of determining a single effective aperture value from the rough surface? For instance, what type of roughness can be dealt with using effective aperture, and in what cases might using an effective value lead to very poor estimates of macro scale behavior? For instance, highly oriented and isotropic roughness, like parallel grooves versus isotropically distributed roughness.
Yeah, Richard, that's an excellent question. That's something that we're starting to look into. I'm working with a postdoc and some other staff members at Los Alamos right now. We're building a new toolbox. It's called SurFrac, where we can generate synthetic fracture surfaces. And so we're using methods like the one proposed by Brown. We have a fractal dimension one in there. And what we're trying to do is essentially build a suite where we can start to put synthetic fracture surfaces into the fracture network. And then at the same time, there are so many closed form expressions for effective aperture that you can have taken the statistics of a surface. And the idea there is essentially we'll look at different statistics of the surfaces, different ways to construct them that might be statistically identical, and see which of the effective models captures that at the macro scale. Because all these models have been kind of like shown to work in some cases on the individual fracture, but not necessarily, I haven't seen them tested at the macro scale to like, can you get back the effective permeability of the system using effective apertures relative to a rough surface? Where I think things are going to be really hard is when you start to look at flow channelization at the individual fracture scale. I don't know how an effective aperture is ever going to capture that. If you have very structured roughness, like you're saying parallel grooves, versus isotropic roughness. Again, I really don't know how an effective model is going to capture that very well. I think we're going to see in some cases when it's isotropic, it's going to do okay. When it becomes highly anisotropic, I think things are going to really break down. But I don't know off the top of my head. I don't have rules of thumb for that yet, but it is an avenue that we're going to.
Thank you. So we have another one. First of all, great. Vivek Pavsar says, great talk, thank you. I was just wondering if you have G as the body force in the governing equation, gravity, I assume. Does that affect the flow and the scale of network? Also, is it possible to see the effect of viscosity variation?
Yeah, so in everything I showed today, we turned gravity off just to keep it simple. We have done some work at the kilometer scale where we've had gravity turned on as a body force. And you can see some effect from it. I mean, it's also very relative to what your driving force is in the system. So whether you have like well pumping or you have just strong pressure gradient, I really, I think the network needs to be fairly large. And then you also have to do like a relative balance of forces with your flow to say whether or not it's going to be a big effect or not. But like within pFlowtran, FEHM, you can turn gravity on and off. So you can do two simulations side by side and see the effect in your network. So it's feasible to check that. I've seen cases where it does matter and I've seen cases where it doesn't. Yes, you can also do this with viscosity. With like the supercritical CO2, it's a different viscosity than the water that it's in. Again, like whatever your favorite flow solver can do, we can start to kind of probe these questions. Both of these, it's open-ended when it matters, when it doesn't. I think there's a lot to explore in terms of like phase diagrams of different behavior as we modify parameters.
I had a curiosity about your velocity reconstruction, where you mentioned, of course, that the system is over constrained. I mean, how challenging is it to solve? And I assume it's very large. And also, what can you say in terms of property of the reconstructed field?
So there's a few ways to do this. One is that you do it locally, right? You just do it at each control volume. And that gives you essentially a piecewise constant velocity field, okay? That's obviously not terribly difficult. You do just a singular value decomposition, invert it, it's fine, right? To do the pseudo inverse, not bad. There's also a way you can do it, which is much heavier, where you solve it as a global system, where essentially you're imposing a divergence-free field over the entire piece. That is obviously much harder to do, because now you have essentially this giant block matrix with each one of these constrained least squares pieces. There's a paper by Lipinoff and Srinivasan from 2012 where they talk about that. And in that case, you can impose getting back a divergence-free field. They more do that with 3D unstructured meshes. You would have to take extra care again at intersections of fractures for that one. But in that case, you would end up with like a divergence-free, still piecewise. I think like a piecewise linear, but I think you could probably push that further in terms of what you can do with the pseudo inverse and optimization to add additional constraints on it. The other thing is that, with the particle tracking, how high of order of accuracy you want to do the interpolation, and you're like, if you want to do like Runge cut at 2 or RK4, they all kind of interplay with each other to see essentially what physics you want to retain in the particle tracking. You can make it as expensive as you want.
Sure. Thank you.
Yeah.
And maybe I have another one while we wait for like the audience. So in the first point that you mentioned that density, the network density, like decreases, affects negatively channelization. And I was wondering, do you think there are like other features, like in a statistical sense of the network, that might affect it? Like, I don't know, the variance
Yeah.
of an average with respect to average orientation or other measures of connectivity.
Absolutely. A big one would be, let's say you are still your network is still the radii follow a truncated power law distribution, right? That decay exponent of that distribution would strongly influence flow channelization, right? Because as that decays slower, you have more big fractures, and you can have these primary conduits that pass through the system. We looked at that a few years ago, and we saw really high channelization that comes from if you have lower decay exponents, particularly if you get below 2. Yeah, so you end up with these like infinite variances in the truncated power law. Well, infinite variances in the Pareto distribution. It's because you're truncated, it's never infinite for that one. But you end up with more and more of these big fractures, and they become these dominant structures that influence more channelization. Yeah, so that is another feature there. I think in that paper, we just wanted to focus on kind of just the density aspect and isolate it from these other pieces. But there's clearly many directions you can expand out from there. That the decay exponent is just another one that we've looked at too.
Thank you. Any other questions from the audience? You can also, I can unmute you and you can ask your questions directly. Don't be shy. Well, okay, here. Jose Castillo asks, how does the model treat the appearance or disappearance of fractures?
It does not. In this case, the fracture network is static. It's generated once, and then it's held. So there's no fracture propagation, there's no growth, there's no closing. We've started to look at geochemical weathering. So fractures can begin to essentially dissolve and become higher permeability, or there can be precipitation and they can become lower permeability. But the actual geometric structure of the fractures in our particular networks do not change.
So they're not allowed to completely close, even if you have compression, there's still something left.
No, there'll always be. That makes the solver very, very mad if they close completely. Yeah, so they don't disappear, and they don't grow, they don't nucleate. There's a lot of really good work on that, and they're called kinetic fracture networks, where you have kind of these like kind of pseudo geomechanical models that grow things, that grow the fractures. And you've done a lot of work on fracture propagation, and especially like the tip point, like the singularities there. It's a hard problem. So as far as these large scale networks, we treat them as generated once and they're static.
Okay, well, I think, well, first of all, thank you once again for giving this very interesting talk. And also I'd like to thank the audience for attending. And you have a good day or evening, depending on where you are.